Okay. All right, let me get to the actual PowerPoint. Okay, so this is where we left off the last time. And just to briefly review what is happening here. What's going on here? Hold on. Okay, so just to review what we're talking about here. This is basically the combustion analysis of something which is organic. And if you remember, I said that organic compounds are compounds of carbon. They usually contain carbon, hydrogen, and oxygen in some cases, and other elements like nitrogen and so on. So let me just go through this quickly. There are three compartments here. The first compartment is the furnace, which will contain your organic compound that you're analyzing. And by the way, just to remind you, organic compounds, when burnt, will produce carbon dioxide and water, right? So in this case here, the furnace is burning the sample here. Oxygen is rushed in here because oxygen is needed to continue the combustion process. Produces carbon dioxide and water, which are led into this compartment, which contains magnesium perchlorate. The role of the magnesium perchlorate is to absorb the water that is produced. And then the increase in the mass of the magnesium perchlorate will give you the mass of the water that is produced. And then, assuming that all the water is absorbed by the magnesium perchlorate, the only thing that would emerge from here would be the carbon dioxide, which would be led into this compartment, which contains sodium hydroxide. And again, a reaction will take place where the carbon dioxide will be absorbed by the sodium hydroxide. So there will be an increase in the mass of the sodium hydroxide, and that increase in the mass will be due to the carbon dioxide. So basically, if you get those data, the mass of the carbon dioxide and the mass of the hydrogen, you can do your calculation backwards to determine the original mass of carbon and hydrogen present in the original compound. And if there are other elements present, then you can do some subsequent calculations to find the mass of those elements. Once you get the mass of those elements, then you can determine the empirical formula. So that's what this example is all about. Let me just skip to the next slide. Okay, so this example right here is a typical combustion analysis problem. So this question says, burning a 0.1000 gram sample of a carbon, hydrogen, and oxygen compound in oxygen yields 0.1953 grams of carbon dioxide and 0.1000 grams of water. And then it says separate experiment shows that the molecular mass of the compound is 90 AMU. So the first question is asking for you to determine the mass percent composition. The B part is asking for the empirical formula. And the C part is asking for the molecular formula. All right, so I'm definitely going to need some more space to solve this problem. So let me, okay. Let me, what shall I use? Oh, you know what? Let me copy this first. And I'm going to use Word. Okay, so this is the question. Scroll up. And let me, okay, so the question says you're starting off with a 0.100 gram sample of the compound, and this is the mass of carbon dioxide that is produced, and this is the mass of water that is produced. All right, so what I would do first is start off with the 0.1953 grams of the CO2, and I would convert that to moles. So how do we do that? We multiply by 1 mole of CO2 above, and the molar mass of carbon dioxide below, which is 44.01 grams of CO2. The next step is to find the moles of carbon, right? Now, based on the formula here, 1 mole of carbon dioxide will contain 1 mole of carbon, all right? And then the next step is to find the mass of carbon. So therefore, that would be the molar mass that I would use here, 12.01 grams of carbon over 1 mole of carbon. And that's basically how to determine the mass of carbon in the original compound. So 0.1953 divided by 44.01 times 12.01. So according to my calculations, this works out to be equal to 0.053, okay, 4 sig figs, 30 grams of carbon, all right? And then I'll do a similar type of calculation, but this time starting off with 0.1000 grams of H2O. So what I would do, like I did in the previous line of calculations here, I'd convert the grams of water to moles, right? So that means I'll have 1 mole of H2O above, and down here, the molar mass of water, which is 18.02 grams of H2O. So that will go with that. And then here, I must emphasize here that what you're going to do here is determine the moles of water. A very common error that students tend to make when they're doing these problems is that okay, let me just say what is happening here. What is happening here is that because of the formula says H2O, that means that there are 2 moles of hydrogen per mole of water. So therefore, you're going to put 2 moles of hydrogen above and 1 mole of H2O below. A common error that students tend to make at this stage is that they forget that there's a 2 here. So they put 1 mole of hydrogen here for every 1 mole of water, but that's not true. It's 2 moles of hydrogen for every 1 mole of water, all right? And then the next step is where we convert the moles of hydrogen to grams. So that's where the molar mass of hydrogen comes in, which is 1.008 grams of hydrogen over 1 mole of hydrogen. So let's see what that gives. 0.1 divided by 18.02 times 2 times 1.008. And according to my calculation, round it off to 4 sig fig, that will be 0.01119 grams of hydrogen, all right? So what we have successfully done so far is to determine the masses of hydrogen and carbon in the original compound. But remember, the question says that there are 3 elements: carbon, hydrogen, and oxygen, right? So the question now becomes, how do we get the mass of the oxygen? Well, we know what the total mass is. The total mass is 0.1000 grams, right? So to get the mass of the oxygens, we take the total mass of that compound and minus from that the sum of these 2, right? So minus 0.05330 grams plus 0.01119 grams, and then we work that out, and that would give us the mass of the oxygen. So 0.1000 minus the sum of 0.05330 plus 0.01119, and according to my calculations, I got I got 0.03551 grams, all right? So now we have the masses of carbon, hydrogen, and oxygen. So the question is asking for us now to determine in the A part, the mass percent composition. Well, let me create some, or let me scroll down here. So to get the mass percent composition of each element, so let's start off with the carbon. Percentage of carbon will be equal to, what's the mass of carbon? 0.05.
12.101.
I'm sorry?
You did 12.01 for carbon?
No, that's the molar mass. We're not talking about that. We're talking about the actual mass, which is 0.05330 that we calculated. 0.05330 grams divided by the total, which is 0.1000 grams times 100%. So that would be equal to 0.05330 divided by 0.1. Okay, so that would be 53.30%. And then we do a similar calculation for the hydrogen, which is 0.01119 grams divided by 0.1000 grams times 100%. And that would be equal to 11.19%. And then for oxygen, percent oxygen, that oxygen, not carbon, and that would be equal to 0.03551 grams divided by 0.1000 grams times 100%. And that would be equal to 35.51%. All right, so those are the percentages of those three elements. And what I like to do is to check to make sure that they add up to 100. Let me do that now. Exactly, they add up exactly to 100%. All right, and that's it. So that's it for the A part. The A part was asking for the percentage of each element, and that's how you do that. All right. Any questions about this? Any questions? Any questions? Okay, now the B part is asking for the empirical formula. Now, in this particular case, there are two ways you could do this. You could use the masses that we calculated here, here, and here, or you can use the percent values. It doesn't matter which one. I'm going to use the percent values, but you could just as well use the mass values. So what I'm going to do to create some space is to get rid of this here. So just like I showed you before, I'll draw a table, carbon, hydrogen, and oxygen at the top of the table. And then, again, I'll assume 100% or 100 grams, which means that the percentage would represent the mass of each element. So carbon is 53.30 grams. Hydrogen is 11.19 grams. And what was oxygen? 35 point what?
35.51
grams. Yeah, okay, good. So those are the masses. So if you remember, the next step would be to calculate the moles. So 53.30 grams multiplied by 1 mole over 12.01 grams. In the case of hydrogen, it's 11.19 grams multiplied by 1 mole over 1.008 grams. And then in the case of oxygen, it's 35.51 grams multiplied by 1 mole over the molar mass, which is 16.00 grams. All right. So let's see here. So for carbon, it's 53.30 divided by 12.01. And according to my calculation, that gives you 4.438 grams. I'm sorry, not grams, moles. And then in the case of hydrogen, it's 11.19 divided by 1.008. And I got 11.10 moles. And then in the case of oxygen, it's 35.51 divided by 16. And according to my calculation, this works out to be equal to 2.219. 2.219 moles. Okay, so those are the mole values for carbon, hydrogen, and oxygen in this compound. The next step is to do what? Can somebody remind me?
Oh, you divide by the least.
Divided by the lowest of these three mole values, right? Which would be the 2.219, right? So you're going to divide right through by 2.219 moles, right? So this becomes 4.438 moles divided by 2.219 moles. Here you're going to have 11.10 moles divided by 2.219 moles. And here, this divided by itself will give you 1, right? So 4.438 divided by 2.219. So that gives you 2 exactly, right? The 11.10 divided by 2.219, that gives you 5.002, which is approximately 5. So therefore, the empirical formula will be C2H5O. And that's it. All right. So that's the empirical formula, which answers the B part. Now the C part is asking for the molecular formula. And in order for you to do that, if you remember, we need to find out what is called the integral factor. So the integral factor, I, is equal to the molar mass, or molecular mass divided by the empirical mass. So the molecular mass is given as 90 AMU. The empirical mass would be the sum of the masses of all of this. So the empirical mass in this case would be 2 times 12.01 AMU plus 5 times 1.008 AMU plus 16.00 AMU. So let's see what that gives. So 2 times 2.01 plus 5 times 1.008 plus 16. So that gives, according to my calculations, 45.06 AMU. So we're going to take that value and put it down here. 45.06 AMU. So 90 divided by 45.06, and that gives 2, which means that the molecular formula will be equal to C2H5O2, which is C4H10O2. That's how that is done. All right. Any questions about this? So this is basically a typical combustion analysis type problem. All right. Let me see here. Okay, let me see. Oh, so in your assignment, let's see if I can find it. Assignment 3. There are a couple of questions. We can just look at one of them and then you can do the rest of that type. Okay. Okay, this question, let me just check something. Okay, this question number 4. It says, after combustion with excess oxygen, a 12.501 gram of a petroleum compound produced 38.196 grams of carbon dioxide and 18.752 grams of water. Previous analysis determined that the compound does not contain oxygen. So this compound only contains carbon and hydrogen, which makes it actually easier to do, all right? So the question is asking for you to establish the empirical formula of the compound. So let me show how that is done. So basically, again, we start off with the mass of each of carbon dioxide and water respectively. Let me start off with the carbon dioxide first. 38.196 grams of CO2. And what we do is convert that to moles like we did before. 1 mole of CO2 down here would be 44.01 grams of CO2. And then the next conversion factor is to convert from moles of carbon dioxide to moles of carbon. So 1 mole of CO2 to 1 mole of carbon, right? Now, in this particular situation, because there are only 2 elements, carbon and hydrogen present, we do not need to take the next step and find out the mass of the carbon, right? And we don't need to do the same thing for the hydrogen. Why? Because we would have needed to do that in order to find the mass of any other element that's present. But since we know that the only 2 elements are carbon and hydrogen, all we have to do is calculate the moles of carbon and the moles of hydrogen. So let's deal with the moles of carbon. 38.196 divided by 44.01. So according to my calculation, this works out to be equal to 0.8679 moles of carbon, all right? And then we do a similar calculation for the water, 18.752 grams of H2O. We convert that to moles. So 1 mole of H2O up top, and down here the molar mass, which is 18.02 grams of H2O. And then the next conversion factor, again, remember that there are 2 moles of hydrogen per mole of water. So therefore, 2 moles of hydrogen will go up here. 1 mole of H2O would go down here. And again, we don't have to find the mass of hydrogen for the reasons I mentioned before. So 18.752 divided by 18.02 times 2. Okay, so according to my calculations, this works out to be 2.081 moles of hydrogen, all right? So those are the only 2 elements present, carbon and hydrogen. So to get the empirical formula, I do my little table thingy here again. And in this case here, we don't need to start off with any masses of carbon and hydrogen because we have the moles already. Oh, I'm sorry, yes, sir.
Wouldn't you round up the 2.081 to 2.082? Because 7 and 7 we rounded up.
No.
No?
Well, according to what I have here, and I just realized something. Because what I have here is 2.08124 and some other digits, so it rounds off to 2.081. So I don't know. Let me do this calculation. 18.752 divided by 18.02
Oh, you rounded out.
times 2.
We used
I never-
18.1016.
Yeah, that's what I used, okay.
Okay, so everything squared away?
Actually, that's my mistake.
All right, so as I was saying, unlike the previous example that I worked where we start off with the mass, we don't need to do that here because we have the mole values given. So we can start off with this row where we have the moles. In the case of carbon, that's 0.8679. And then for hydrogen is 2.081 moles. And then we divide by the lowest of the 2 mole values, which would be the 0.8679 moles. So this divided by itself will give you 1, and then you're gonna have 2.081 moles divided by 0.8679 moles. So let's see what that gives. 2.081 divided by 0.8679. And according to my calculations, this works out to be equal to 2.40. Actually, hold on. What am I saying? Round up to 4 sigfigs, so that would be 2.398. All right. So now, obviously, this number here is not close to an integer, right? So we can't just round it off to the nearest integer. So basically, we have to multiply both of these numbers here by a number which will convert this into an integer. And it looks like I have to do some trial and error thing here. So let me see here. So 2.398. I'm going to multiply by 4. Let me see what that gives. That looks like it works. Oh, no, this works even better. I multiply by 5.
Yeah.
Yeah, that works better. Yeah. Because when I multiply both of these by 5, let me create some space here. Okay, what I'm going to do is continue the bottom of this table up here, right? I'm going to multiply right through by 5. That means that for carbon, this will become 5. And for hydrogen, this will become 11.99, which is approximately 12, right? So therefore, the empirical formula for this compound would be C5H12. And that's how that is done, all right? Okay, any questions about this one? Any questions? Any questions? All right, so if you understood the example I worked earlier and this one, then let's see here. You should be able to do, let me clear this here. You should be able to do number 5, number 6, number 7. Okay, so yeah, do those on your own. And if you have any issues, problems with those, let me know. And I can help with that. All right, so let's go back to the PowerPoint. And let's talk about chemical equations, writing chemical equations. And again, this is something that you would have encountered in your introductory or high school chemistry. We all know that a chemical equation is basically a shorthand way of representing what happens in a chemical reaction. Any typical chemical equation will have the symbols for the reactants on the left, the symbols of the products on the right, and you have an arrow going from left to right, and you may have some additional information that is placed above or below the arrow. So for example, if you see a triangle, that represents elevated temperature, or you might see an actual value for the temperature that's given, or actually the value of other conditions like pressure and so on, all right? So, so that's that. Now, one thing about equations which must be done in order for it to be useful is that it must accurately represent the quantitative relationships that occur in the reaction, all right? So basically, in other words, we say that the equation has to be balanced, right? And when we say that it's balanced, basically what we mean is that the equation must be written such that the number of atoms of element on each side would be the same, all right? So an example, a simple example is given here, where you're given an equation which is not balanced, H2 plus O2 to give you H2O, and it's not balanced because even though you have 2 hydrogens on this side, you have 1 here, right? Based on that fact alone, without even looking at anything else, we can conclude that the equation is balanced. So the task is to balance it. Now, there are a couple of ways that you should not go about balancing it. One, you don't just arbitrarily add an atom that you would need to balance it on either side, right? Can't do that, right? That's not a legitimate way of balancing an equation. Another thing you can't do is change the formula for any of the substances involved on paper to achieve the balance, which is what is done here, right? What they did here is just put a subscript of 2 here to convert water to hydrogen peroxide on paper, right? Can't do that, right? Basically, whenever you're balancing the equation, what you need to do is make sure that you make changes to the coefficients, the numbers that are placed in front of the formulas in order to achieve that balance. And what you're going to see, especially for some of these equations which are more complicated, you have to go back and forth in terms of making those changes. So in this particular case, you're given this unbalanced equation. What I would do is I would look at the hydrogens first, and I see that the hydrogens are already balanced, right? And then I look at the oxygens, and I see that the oxygens are not balanced. I have 2 here, I have 1 here. So the question is, how do you go about balancing oxygens? And the answer is that you place a 2 in front of the H2O here, right? Now, by placing a 2 here, you're balancing up the oxygens, but you're also doubling the number of hydrogens here, right? And as a result, you have 4 hydrogens here, but you have only 2 here. So basically, to achieve that balance for the hydrogens, you put a coefficient of 2 in front of the H2. And now the equation is balanced, all right? So that's a relatively simple example, but that what I've just shown you is basically how you go about balancing an equation. You just basically look on one side to the other in terms of the respective elements, and you make adjustments to the coefficients in order to achieve that balance. Okay, so with that said, let's just go through some guidelines for balancing equations. It says here, if an element is present in just one compound on each side of the equation, try balancing that element first. And then it says balance any reactants and products that exist as free elements last. If you have polyatomic ions present, then in some cases, what you'll find is that if those polyatomic ions exist on both sides, then you can treat that as one unit, as if it's an element by itself, all right? And then the next one is that at times an equation can be balanced by first using a fractional coefficient. Then that fraction is cleared by multiplying the coefficient by a common factor. I think we're going to see an example of that shortly. So here are some examples. Basically, you're asked to balance these equations. And the first one is Fe plus O2 to give Fe2O3, all right? So let me change the color of this thing here. So what I would do is I would look at the iron first on both sides. You have iron here, iron here. You have 2 iron atoms here. You have 1 here. So what I would do is put a 2 here. All right. Then we look at the oxygens. I notice that there's 2 here and that we have 3 oxygens on the right side. So what I would do here, this is where you can use a fraction to balance the equation. What I would do is put 3 over 2 here, right? Because 3 over 2 times 2 gives you what? 3, which balances with the 3 oxygens. However, this is not the end of the solution to the question because you need to get rid of this fraction. And the way you do that is that you multiply the entire equation right through by 2, right? So when you multiply right through by 2, you're going to end up with 4Fe plus 3O2 to give 2Fe2O3. And that would be the final answer. All right? So that's how I would go about balancing that equation. Okay, any questions about this one? Any questions? Any questions? Let's look at the next one. Okay, so if you look at the next one, you notice that there are 2 carbons here. There's only 1 here. So what I would do is put a 2 here. And then you notice that there's a 6 here for the hydrogen, but there's only 2 here. So what I'll do is put a 3 here. All right? So now we get to the oxygens. How many oxygens do we have on the left side? We have 2 total, right? How many do we have on the right side? 4 plus 3, 7 total, right? So the question now becomes, how do we balance the oxygens, right? Well, because you have 7 total on the right side, what I would do is multiply the oxygen on the left side by 7 over 2. Because 7 over 2 times 2 gives you 7, right? And then, again, to clear that fraction, we have to multiply the entire equation by 2. So the final answer would be 2 C2H6 plus 7O2 to give 4CO2 plus 6H2O. And that would be the final answer. All right? Any questions about that one? Any questions? Okay. For the next one, you're given H3PO4 plus sodium cyanide to give hydrogen cyanide and sodium phosphate. All right, so let's see here. Okay, first thing I noticed, there are 3 hydrogens here, and there's 1 here. So what I would do is put a 3 here, and then there's 1 phosphorus. So the phosphorus is balanced, and the oxygens are balanced. Then we get to the sodium. The sodium is not balanced because we have 3 here, and we have 1 here. So I'll put a 3 here, and then the carbons, let's see, we have 3 carbons here, 3 carbons here, and we have 3 nitrogens here, 3 nitrogens here. So now the equation is balanced. All right? And that's how that is done. Okay? All right, any questions about this one? Any questions? Questions? All right, so based on what we've just done, let me just look at the assignment. Okay, so you should be able to do question 8 and 9. Okay, yeah, questions 8 and 9. All right, so make sure you do those on your own time. Okay, so let's go back to the PowerPoint. And okay, so here's where we get to the reason why it's important that we work with balanced equations when it comes to doing some stoichiometric problems, right? Because once you have the equations balanced, the coefficients basically helps you to determine the relative proportions of the substances involved in a reaction, all right? So an example is given here, the reaction between carbon monoxide and hydrogen to form methanol, right? So that equation is balanced, right? And based on the balanced equation, and more specifically, based on the coefficients in the balanced equation, we can establish mole relationships between any 2 substances involved, right? So as stated here, 1 mole of carbon monoxide is equivalent to 2 moles of hydrogen, right? Because you have a 1 here for carbon monoxide and 2 for hydrogen, right? You can also establish the relationship between carbon monoxide and methanol, that's 1 to 1. And in the case of the relationship between hydrogen and methanol, that's 2 to 1. All right, so it's important that you establish those because those numbers will help you to do the type of calculations we're going to do. Now, based on those relationships, we can write down what are known as conversion factors, or in the notes here, it's called stoichiometric factor or mole ratio. Same thing, right? Basically, the mole ratio is expressing the relationship between the mole relationship between 2 substances involved in a reaction as a fraction. All right. So, for example, the mole ratio between carbon monoxide and hydrogen can be expressed as 1 mole of carbon monoxide divided by 2 moles of hydrogen. All right. Or you can flip it, right? You can have 2 moles of hydrogen above and 1 mole of carbon monoxide below. Now, which one you use is dependent on the type of problem that you're trying to solve, and you're going to see that shortly. Some others are shown here. For example, the relationship between carbon monoxide and methanol can be expressed like this: 1 mole of carbon monoxide above as the numerator and 1 mole of methanol below as the denominator. And then the relationship between the hydrogen and the methanol can be expressed like this: 2 moles of hydrogen over 1 mole of methanol, or the other way around again, depending on the kind of problem that you're trying to solve, all right? So you're gonna see how these conversion factors, mole ratios, if you will, the role they play in terms of solving stoichiometric problems. Now, whenever it comes to solving stoichiometric problems, basically it comes down to this right here that you see on the screen. If you have the moles of one substance and you multiply by the correct mole fraction, right, that will give you the moles of the other substance involved in the reaction, all right? So you'll notice the way this is set up. You have moles of B divided by moles of A because you want this unit to cancel the moles of A here, and that gives you the remaining unit, which would be the moles of B. Now, in some of the more complicated problems, you might have some preliminary steps that you take to get to moles of A, right? And also, you might have some subsequent steps from moles of B that you need to calculate. Again, it all depends on how the question is worded, as you're going to see shortly. In fact, here's one example, and this one is a relatively simple one. So fortunately for us, they gave us a balance equation, right? And the question says, when 0.105 moles of propane is burned in an excess of oxygen, how many moles of oxygen are consumed? And it gives you the balance equation, right? So basically, you're going to start off with what you're given, which is 0.105 moles of propane, which is C3H8, all right? So we have to convert that to moles of oxygen. That's what the question is asking for. Now, based on the balance equation, there's a 1 to 5 mole ratio between the oxygen and the propane. So the way we represent that here is that we put 5 moles of oxygen above as a numerator in that conversion factor, and down here, 1 mole of propane, C3H8 below as the denominator. So this will cancel out with that, and then we do the calculation, which is 5 times 0.105, which is that. So that would give you 5 times 1.05, which would be 0.525 moles of oxygen. And that's how you do that. All right? Any questions about this one? Any questions? Any questions? Okay. So this here that I have on the screen is basically an outline of how you go about solving a typical stoichiometric problem where masses are involved. Now, the problem that we just looked at, we're going from mole to mole, right? One step, no problem, because the mole ratio gives you that relationship, the mole relationship between two substances. But when you start off with, or if you're given the mass of one substance, then it's not as straightforward, right? Because you'd have to convert, for example, let's say you're given a certain amount in grams, you'd have to convert that to moles before you do the mole ratio. And then if the question is asking for the mass of the other substance, then you have to convert the mole of that value to grams to get your answer. And that's what this outline is all about. You're saying that, okay, let's say you're given the grams of substance A, right? What you have to do first is convert that to moles. So that's why you multiply, or I should say divide by the molar mass to get the moles of substance A, right? Then we use the mole ratio established by the balance equation to go from moles of A to moles of B, right? And then, depending on the question, if you're asked to get the mass of B, then you'd have to multiply the moles of B that you got here by the molar mass of B to get the grams of B, all right? So it all depends on the information provided and what the question is asking for, all right? Okay, as stated here, both substances A and B, they could be two products or two reactants, or one could be a reactant and the other one could be a product, right? And there's a question being asked here. It says, think, if we are given moles of substance A initially, do we need, oh, okay, so they're asking, if you're given a moles of substance A, do we need to convert A to grams? And the answer is no. Because if you're given a substance, if you're given a mole of substance A, then all you have to do is use this to get the mole of substance B, right? And then do the rest if the question is asking for that, all right? Okay, so with that said, let's look at these two examples. So again, I'm going to need some space, so let me do this. Let me copy the first one here and post it in the Word document that I have here. Okay, so let me just all right, so this is the question. The final step in the production of nitric acid involves, oh, let me clear this here. Okay, so the question says the final step in the production of nitric acid involves a reaction of nitrogen dioxide with water, and then it says nitrogen monoxide is also produced. How many grams of nitric acid are produced for every 100 grams of nitrogen dioxide that reacts? So the first thing you need to do is to figure out what the balance equation is, right? And let me just say this. You cannot solve a stoichiometric problem without a balance equation, right? So in some cases, you might be given a balance equation that makes your life a lot easier. In some cases, you might be given an unbalanced equation, in which case you have to balance it. And yet in other cases, as in this case, you might be given a description of the reaction in words. And based on that information provided, you have to figure out what the balance equation is, right? So if you look at the question carefully, the way it is stated, it says that the production of nitric acid involves the reaction of nitrogen dioxide with water. So there are two reactants involved, NO2, and, okay, what is going on? O2 plus water, right? Those are the two reactants. And then continuing with the question, let me see here. Okay, so one of the products would be nitric acid, and the other product would be nitrogen monoxide. All right? So that's basically the unbalanced equation. So now we have to balance it. So how do we balance it? Well, let's see here. We have one nitrogen here. We have two nitrogens here. So I'm going to put the 2 here. And then we have 4 plus 1, 3 oxygens. Okay, there are 2 hydrogens here, 2 hydrogens here. And then let's see now. 4 plus 1, 5. 2, 3, 6. Plus 1, 7. Let's see here. 2 hydrogen. 2 hydrogen, 2 nitrogen. Oh no, the nitrogens change up. Let me see here. We have 2 nitrogens here. So if I were to change the 2 to 3, let's see what happens. Okay, now it's balanced. Because now we have 3 nitrogens, 2 plus 1, 3 nitrogens. We have 6 plus 1, 7 oxygens. 2 times 3 plus 6 equals 6 plus 1, 7. And then 2 hydrogens. Okay, so now the equation is balanced, all right? So that's the first thing you have to do. You have to make sure that the equation is balanced. Okay, so the question is asking how many grams of nitric acid are produced for every 100 grams of nitrogen dioxide that reacts. So we're going to start with 100 grams of NO2, and we're going to convert that to moles. So 1 mole of NO2 down here, and the molar mass of nitrogen dioxide, which is molar mass of NO2, which would be 14.01 gram per mole plus 32.00 gram per mole, which would be equal to 46.01 gram per mole. So down here, I'm going to put 46.0 grams, 0.01 grams of NO2 down here, all right? So this will go with that. And then the next step is to look at the mole ratio between the nitric acid and the NO2. And based on the balance equation, that's a 2-to-1 ratio. So 2 moles of HNO3 would go above. And down here would be 3 moles of NO2. And then the last step, by the way, this will cancel out with that, is where we go from moles of nitric acid to grams. So 1 mole of HNO3 would go down here. And for the molar mass of HNO3, that would be equal to 1.008 grams per mole plus 14.01 grams per mole plus 3 times 16.00 grams per mole. So let's see what that gives. So okay, so I got this being equal to 63.02 grams per mole for the nitric acid. So that goes here. So let's do the number crunching. 100 divided by 46.01 times 2 divided by 3 times 63.02. And according to my calculation, this works out to be equal to 91 point, how many sig figs? 4 sig figs, so 91.31 grams of HNO3. And that's how that is done. All right, any questions about this one? Any questions? Okay, so let's look at the other example. Is it okay for me to clear all this? All right, let me lasso this here. And let me go back to the PowerPoint. And now I'm going to copy this right here and paste it onto the Word. All right, so this question says ammonium sulfate, a common fertilizer used by gardeners, is produced commercially by passing gaseous ammonia into an aqueous solution of 65% sulfuric acid by mass and has a density of 1.55 grams per mil. So the question is asking how many mils of this sulfuric acid solution are required to convert 1.00 kilogram of ammonia to ammonium sulfate. All right, so what I would do is first write down the equation. Again, whenever you're doing any stoichiometric type problem, establish a balance equation first, right? So the equation in this case is going to be NH3 plus H2SO4 to form NH4 2 SO4, all right? And to balance this, we're going to need a 2 here, and that's it, right? So that is the balance equation, all right? So the next step is I'll start off with the 1.00 kilograms of ammonia. And what I would do first is convert that to grams. So that would be 1 kilogram of ammonia below, 1,000 grams of ammonia above. So this will go with that. And then the next conversion factor would be to convert from grams to moles, right? So for ammonia, nitrogen is 14.01 grams per mole plus 3 times 1.008 grams per mole. And this would give you the molar mass of NH3. So let's see what that gives. 1.008 times 3, and then I add 14.01 to that. So I got 17.03 grams per mole. So the way I'd represent that here is that I'll put 17.03 grams of ammonia for every 1 mole of ammonia. All right? Okay. Next step is to look at the mole ratio between the ammonia and the sulfuric acid. That's a 2-to-1 mole ratio, right? So the way I would represent that here is I would put 2 moles of NH3 down here as the denominator, and 1 mole of H2SO4 above as the numerator, right? So that this unit will go with that unit. So now up to this point, we would have determined the moles of sulfuric acid. But remember now, the question is not asking for the moles, it's asking for the milliliters of sulfuric acid that would contain that much moles, right? Now, how do we determine that? Well, we're given some additional information here. We're given that the percentage of sulfuric acid in the solution is 65%, and we're given that the density of this solution is 1.55 grams per mil, right? Now, based on the 65% sulfuric acid information here, what this tells you is that for every 100 grams of the solution, 65% or 65 grams of it would be sulfuric acid. So we can, there's one step I need to do first before we get to that. Okay, this step would involve getting the mass of the acid. So 1 mole of H2SO4 would be down here, and above would be the molar mass of sulfuric acid. Let me do that calculation here. Molar mass of H2SO4. That would be equal to 2 times 1.008 grams per mole plus sulfur, which is 32.06, right? Yeah. Plus 4 times 16.00 for the oxygens, grams per mole. Okay, so let's see what that gives. So 2 times 1.008 plus 32.06 plus 4 times 16, that's 64. So according to my calculation, this works out to be 98.08 grams per mole. All right, so that's what I'm going to put here, 98.08 grams of H2SO4. So we needed to do that first. All right, now we get to the 65%, because as I was saying, 65% means that for every 100 grams of the solution, 65 grams of that would be sulfuric acid, right? So the way I can represent that here is that I'll put 100 grams of solution above and 65 grams of H2SO4 below. All right, so that this would go with this. And I'm running out of space, and I'm just continuing down here. So the next conversion factor now is where we convert, where we get the grams of the solution and convert it to milliliters, which is what the question is asking for. How do we do that? Well, that's why they gave us a density, right? The density gives you the mass in grams per mil, right? So the way I'll represent that here is that I'll put 1 mil above of the solution, and down here I would put 1.55 grams of the solution, so that this unit would go with that unit. And then we do the number crunching. So we start off with 1 times 1,000 divided by 17.03 divided by 2 times 98.08 times 100 divided by 65 divided by 1.55. So according to my calculation, now how many sig figs do I need to roll this out? Okay, looks like I have to roll this out to 2 sig figs. So the answer here is 2,900, round out to 2 sig figs, milliliters of solution. And that's how you do that. All right. Any questions about this one? Any questions? Any questions? No questions? All right. Let me just see what's up next. All right. Let me do this. Let me see. Okay, so based on what we have done, you should be able to do number 10. Okay, hold on. Let me go back up a bit here. Oh, okay. So number 10. Okay, we can't do number 11 yet because we have to talk about limiting reactants. Okay. Now I just remembered, you had reminded me that I missed talking about what was it again? Acids, naming acids. So let me go back to that and then we'll get back on track here, right? So okay, there are several approaches I could take when it comes to naming acids. So what I'm going to do is I'm going to I am going to start off by taking the approach of naming acids according to their anions, or the anions that will be formed. The anions that will form the acids. All right, so okay, so the first type of acid we're going to talk about are what are known as binary acids. All right, and binary acids basically contains hydrogen plus one other element. All right. So the way we name these acids, I'm just going to write down the rule first, and then I'm going to go into some examples. So in terms of naming these acids, naming binary acids, we start off with hydro, then the stem of the name of the other atom, and then IDE. All right. So for binary acids, for all binary acids, we start off with hydro, the stem of the name of the other element, and then the IDE ending. All right. So let me do a couple of examples. So for example, HBr. All right. Now this compound is a gas, right? No, ordinarily, we would call this hydrogen bromide. All right. But when you add it to water to form HBr aqueous, this is now called hydrobromic Oh, okay, my bad. I'm jumping the gun a bit. Let me take this out. I made a big mistake. This is not, what I just said here is not for naming binary acids, it's for naming binary hydrogen compounds. So let me correct that. I'm sorry about that. Let me naming binary hydrogen compounds. All right. So in the case of HBr, let me erase this here. You know what, let me just leave that as it is. Okay, so this is called hydrogen bromide. And by the way, this should be hydrogen here as well, all right? So you'll notice we start off with hydrogen, then the stem of the name of the bromine, and then IDE, right? So hydrogen bromide. Here's another example. This is also a gas, a very awful smelling gas, actually. This is called hydrogen sulfide. All right? Again, you see it follows the rules here. Hydrogen, then the stem of the name of the other atom, and then IDE. All right? And you can apply this to other similar type of compounds. All right? Now, here's the thing. When these compounds are dissolved in water, it produces a solution which is acidic. So in this case, you're going to end up with HBrAq. And in this case here, you're going to end up with H2SAQ. All right? So the rules for naming the acidic solution is different from the rules for naming the original hydrogen compound, right? So let me put in this corner right here the rules for naming binary acids, right? And this is where the hydro comes in. So basically, it's hydro, well, for binary acids, let me write that down first. For binary acids, the rule is that you start off with hydro, then the stem of the name of the other atom, and then ic acid. All right? So hydro, the stem of the name of the other element or the other atom, and then ic acid. So if you apply this that I've just said, the HBr aqueous, this will become hydrobromic acid. And this one will be called hydrosulfuric acid, and so on and so forth, right? So as you can see, naming the acid that is formed from the binary hydrogen compound from the originally here, right? This one is called hydrogen bromide, but when you add it to water, the resulting solution is called hydrobromic acid. In this case here, it's called hydrogen sulfide, but when you add it to water, it becomes hydrosulfuric acid, right? And you can see, you can apply this to other similar type of solutions, all right? Okay, so that's the rule when it comes to binary acids. Now, when it comes to oxyacids, let me clear all this here. So when it comes to oxyacids, as the name suggests, oxyacids, in fact, let me write this down here. Oxyacids contain hydrogen, oxygen, and one other element. All right? So that's what oxyacids are. They contain hydrogen, oxygen, and one other element. All right? So the way I'm going to go about showing you how to name oxyacids, I'm going to start off with the ions from which they're formed. All right? Now, I'm thinking of how to construct this table. Okay, so in one column, I'm going to say ion and then ion name. In fact, hold on. I'm trying to get myself organized here. Let me start off with ion name in the first column. All right? Ion name, then the ion. And then the corresponding acid. Okay, I think this will work. And then the acid name. All right? Okay, so the first ion I'm going to draw right here, a polyatomic ion, is NO2, is the nitrite ion. So that's the name, nitrite, all right? The formula for the ion is NO2 minus, all right? Now, to get from the ion to the corresponding acid, you have to add a hydrogen ion to the structure of the nitrite, right? So you're going to end up with HNO2. So that would be the formula for the corresponding acid. The name of this acid, please note that the name of this acid is nitrous acid. All right? So basically what this rule says is that if the ion names end with ITE, then the corresponding acid name ends with OUS acid. All right? So this is the ion name, and this would be the corresponding acid name. All right? If the ion names end with ITE, then the corresponding acid name ends with OUS acid. All right? So nitrite becomes nitrous acid. Now, here's another example. The sulfite ion. The formula for that is SO3 2-, right? Now, the formula for the corresponding acid is where you add 2 H plus, because you have 2 negative charges here. That means you're going to need 2 hydrogen ions to add to it to form, not SO4, SO3, to form the corresponding acid, right? So if the nitrite becomes nitrous acid, then what do you think the name of the corresponding acid when the sulfite is converted to an acid? Sulfurous acid, all right? Again, OUS acid, the ending, all right? So that's basically how you deal with these acids that are formed from ions whose name ends with ITE. In those cases, the corresponding acid name ends with OUS acid, all right? Now, there's another type of oxyacid, let me just draw a line here, whose names end with ATE, right? 8, right? When that happens, the name of the corresponding acid will end with ic acid. All right? So let me give a couple of examples here. This ion here, NO3-, I'm sorry, wrong color. This ion, which ends with NO3-, the name of this ion is a nitrate ion. Right? So to get from the nitrate to the corresponding acid, we add an H plus, that becomes HNO3. And therefore the name of this acid is nitric acid. All right? So that's what happens in that case, right? Now, here's another example. The sulfate ion formula is SO4 2-, right? And if you were to convert that to the corresponding acid, the formula becomes H2SO4, right? And in this case here, the name of the corresponding acid would be sulfuric acid, all right? So basically, if the ending of the anion ends with ATE, then the corresponding acid name ending would be ic acid. If the end of the name of the corresponding ions end with ITE, then the name of the corresponding acid will end with OUS acid. All right? So that's basically it as far as naming acids, excepting one more thing I need to say. Now, there is one particular acid which is kind of unique, which does not fall into the category of either oxyacids or binary acid, and that is this acid right here. Now, HCl, aqueous, all right? Now, this here can be formed from HCN, gas, right? This is known as hydrogen cyanide. Now, the thing about the acid that is formed, cyanide, when you add water to this, or add it to water, that acid, HCN aqueous, it's not an oxyacid because there's no oxygen in it, right? And it's not a binary acid because it has 3 elements, not 2, right? So what the powers that be, IUPAC, whoever, decided was that they treat it as a binary acid, right? So if you treat it as a binary acid, the name of this acid is hydrocyanic. So this is kind of unique among the acids, among the common acids that you're going to deal with, right? It's not an oxyacid, right? And it's not a binary acid, all right? So they just decided, okay, let's put it in the category of binary acids and name it as such. All right? And that's it. That's it when it comes to naming acids. So basically, you should be able to answer. There was one question in assignment 2 where you're given a list of acids. I think in one case, you're given the formulas and you're asked to give the name and vice versa, right? So based on what we have just covered, you should be able to do those questions. All right? Okay. So let me go back to the PowerPoint. And let's see here, what next? Okay, so now we're going to get into a discussion of limiting reactants, all right? So what you'll find is that in most cases, whenever you have a reaction taking place or somebody's trying to conduct an experiment where they're performing a reaction to produce a product, more than likely, in order for the reaction to work in practice, is that you have to have an overwhelming amount of one particular reactant compared to the other, right? In order to push the reaction to form a product, right? So at this juncture, it's now important for you to understand the difference between what is known as the limiting reactant and what is the excess reactant. The limiting reactant is the one that is completely used up in the reaction, right? So if you think about a reaction taking place, as I said before, in order for the reaction to be successful, you need to have an excess of one of the reactants. Then that means that the other reactant would be the limiting reactant and would be completely used up. And the reason why it's called a limiting reactant is because that reactant limits the amount of product that you're going to end up with eventually, right? So any calculation of the amount of product that you expect to get would be based on the amount that you start off with of the limiting reactant, all right? Once you establish what the limiting reactant is, all the other reactants are in excess, all right? Now, key thing that is mentioned here is that a limiting reactant is not necessarily the one that is present in the smallest amount, all right? So I'm going to use a non-chemistry example right here to illustrate this whole concept of limiting reactant, right? So let's say you're given a task of preparing a lunch, which consists of a sandwich, 2 cookies, and 1 orange. So this is basically an equation. 1 sandwich plus 2 cookies plus 1 orange would give 1 lunch unit, 1 packaged meal, right? So that's basically the combination that is used to formulate this, right? Now, let's say that you have at hand 10 sandwiches, 18 cookies, and 12 oranges. The question is asking, how many of these meals can we make from this combination right here, all right? Now, if you look at things from the standpoint of the 10 sandwiches, okay, what's going on here? Oh, okay. So if you look at things from the standpoint of the 10 sandwiches, okay, let me write down the amounts that you actually have. You have 10 sandwiches here, you have 18 cookies, and you have 12 oranges, all right? So let's say that you look at things from the standpoint of the 10 sandwiches. Based on this combination right here, 1-to-2 ratio, right? If you're going to use up all the 10 sandwiches, you're going to need 20 cookies, right? But you don't have 20 cookies. You have 18, right? So you won't be able to use up all the 10 sandwiches. If you look at things from the standpoint of the oranges, right? You have 12 oranges. That means that you're going to need 24 cookies. You don't have 24 cookies, you have 18. So you won't be able to use up all the oranges. Now, if you look at things from the standpoint of the 18 cookies, right? That means that you're going to need 9 sandwiches, right? You have more than 9, you have 10. So that works out. And then you're also going to need 9 oranges. You have more than 9, you have 12, right? So therefore, in this context, the cookies would be the limiting item. And therefore, you can say that the amount of packaged meals that you can get with the 18 cookies, the 10 sandwiches, and the 12 oranges would be 9, all right? So that means that the cookies will be the limiting item, and that means that the sandwiches and the oranges would be in excess, all right? Because you're going to have leftover after all the cookies have been used up, right? So that's basically the concept that is behind determining what the limiting reactant is in an actual chemical reaction. Here's another example, I think. Let me see here. Okay, now this is an actual chemical situation, chemical reaction. So in this case here, the reaction that we're performing is, let me see if I can squeeze it down here, C2H4 plus bromine to give C2H4Br2. All right, so that's the equation. And this equation is made simple because it's a 1-to-1-to-1 ratio right throughout, right? Now, in this case here, we are mixing 28 grams of ethylene, C2H4, which is 1.0 moles, with 128 grams of bromine, which is Br2, right? So 1.0 moles of ethylene and what was it? 0.80 moles of bromine, right? So these are the amounts that we have initially. Because it's a 1-to-1 ratio, right? We can tell easily what the limiting reactant is. Because that limiting reactant would be this, right? Because you have less of this than this, and it's 1-to-1 in terms of the reaction, right? So what that means is that all of this will be used up, right? So basically the change here would be minus 0.80 moles, right? So that means that 0 moles of bromine will be used up. At the same time, the amount of ethylene that would be used up would be 0.8. So minus 0.80 moles would be the change. So therefore, 1 minus that would give you 0.20 moles, right? So therefore, this would be the excess reactant, and the bromine would be the limiting reactant. And because bromine is a limiting reactant in this case, it determines how much product you expect to get, right? And because there's a 1-to-1 ratio between the bromine and the product, that means that the amount of product you expect to get here would be the same as the amount of bromine that reacted, which would be 0.80, right? Moles. So this underscores a point that the limiting reactant is not necessarily the one that is in greater amount in terms of mass. It's looking at the mole-to-mole relationship and to see which one would be the one that would be used up based on that. And things can be complicated further if it's not 1-to-1, right? In this case, it's made easy because it's 1-to-1. You can easily see that, okay, the one with the lesser amount in terms of moles will be the limiting reactant. But in other cases, that's not the case, all right? In fact, we're going to see shortly a situation where it's not a 1-to-1 ratio between the reactants, and therefore you have to take an additional step to determine which is the limiting reactant. Okay, let's talk about recognizing limiting reactant problems. Firstly, for limiting reactant problems, obviously you need to have at least 2 reactants, right? If you have only 1 reactant, then that reactant would be the limiting reactant, right? But if you have 2 or more reactants, then you have to determine which one is limiting, all right? Then what you have to do is solve the problem by doing a stoichiometric calculation to figure out how much product you expect to get based on each reactant, right? And then after that, once you determine which one produces the lower amount of product on paper, then that reactant would be the limiting reactant, all right? And then you might be asked to do some extra calculations where you're asked, for example, to determine the amount of excess reactant that remains. We're going to see an example of that. In fact, here's the example right now. All right, so let me copy this as well, since I'm going to need a space. Oops. Okay, so let me paste this in here. Okay, so here's the question. The question says, magnesium nitride can be formed by the reaction of magnesium metal with nitrogen gas. So the A part is asking how many grams of magnesium nitride can be made in the reaction of 35.00 grams of magnesium and 15.00 grams of nitrogen. And then the B part is asking how many grams of the excess reactant remain after the reaction. All right, so what's the first thing you need to do? Equation, the balanced equation. Okay, so based on the information provided, what would be the reactants? Or more specifically, what would be the formula for the reactants? based on
Magnesium and nitrogen.
magnesium and nitrogen. Okay, so the formula for magnesium is what? Mg,
Yeah.
and what's the formula for nitrogen?
And
N2, very important. I don't think did I have any one of you in my class in intro? You too, right. You should remember that there are 8 elements that exist as diatomics. Remember I said that, right?
Okay.
So for the rest of you, for the benefit of for the rest of you, just in case you haven't been exposed to that information, the 8 elements are nitrogen, oxygen, hydrogen, fluorine, H2 by the way, fluorine, bromine, chlorine, and iodine. All right, please remember that those elements exist in nature as diatomic molecules. So if you're given a question like this and they say magnesium reacts with nitrogen, N2 would be what you'd use in the formula, right?
I think there's only 7 up there.
Hmm?
Because 7 is one more. You said,
No, that's 7, right?
you said
1,
8
2,
though.
3, yeah.
You said, is there 8 of them or 7 of them?
No, 7.
Oh.
Or did I say 8?
You said 8.
Oh, my bad, 7. Right, so remember, and also while I'm at it, there's one element that exists as 3 atoms per molecule, that's P4, phosphorus, and then there's sulfur, which exists as S8, right? So for my students in intro, I make sure let them know that they need to remember that, all right? Okay, so what was I saying now? Okay, so those are the reactants. So what would be the product? Again, based on the information provided in the question. What would be the product? And there's only one product.
Magnesium nitride.
Magnesium nitride. So what would be the formula for magnesium nitride? And you may need to use that table which has the list of ions, list of common ions. And what I would do is look up the formula for magnesium ions and then look up the formula for the nitride ion. So what's the formula for the magnesium ion? Let me do it up over here.
Mg+2.
Mg 2 plus or plus 2, doesn't matter, yep. And then what's the formula for the nitride ion? Nitride. Don't confuse nitride with nitrite. 2 different. Nitride,
-3.
N3 minus. Okay, so how do we put this together to get the formula?
Mg3
and
and 2.
Mg3 and 2, exactly. So that would be the sole product of this reaction. Okay, then we need to balance it. How would you go about balancing this equation?
I'll put 3
3
reactants.
Mg.
Exactly,
That's it.
and that's it. That's all you need to balance it. All right, very good. So that's the first thing we need to get done before we can do anything else, right? Okay, so the question is asking, how many grams of magnesium nitride can be made in the reaction of 35.0 grams of magnesium and 15.0 grams of nitrogen? So this is the way I would go about doing it. I would start out with the 35.0 grams, 0.00 grams of magnesium, and then I would convert that to moles, right? So 1 mole of magnesium would go up top, and then below would be the molar mass, which is, can you confirm, I think it's 24.31 for the magnesium, or that's correct? 24.3, okay. 24.31 grams of the magnesium, right? And then now I would look at the mole ratio between the product, which is the magnesium nitride, and the magnesium. And you can clearly see that's a 1:3 mole ratio, right? So up top, I'm gonna put 1 mole of Mg3N2, and below I'm gonna put 3 moles of Mg. All right? And then I'll work this out. So 35 divided by 24.31 divided by 3. Okay, so according to my calculation, that would be 0.4799 moles of Mg3N2, all right? So this mole value that we get here is based on one of the reactants, the magnesium. So we have to do another calculation based on the other reactant, a similar calculation based on the other reactant, which is the 15.00 grams of nitrogen. So like we did in the first step here, we're gonna find the moles of nitrogen, which is, we get that by dividing the mass by the molar mass. Now, nitrogen is 14.01 times 2, so that would be 28.02 grams of nitrogen, so that this goes with that. And then we look at the mole ratio between the nitrogen and the product. And it's a 1-to-1 mole ratio. So 1 mole of Mg3N2 above, and 1 mole of N2 below. So let's see what that gives. So that's 15 divided by 28.02. So according to my calculation, I got 0.5353 moles of Mg3N2. So we have these two numbers here. What we do is decide on which one is of the lower value. That would be this, right? Which would mean that the magnesium is the limiting reactant or reagent, yeah. Same terminology, right? Based on the calculation here, the magnesium would produce a lower amount of the product compared to the nitrogen. So therefore, the magnesium would be the limiting reactant. But we're not finished yet, because the question is asking how many grams of magnesium nitride. So what we're going to do is take this number here, 0.4799 moles of Mg3N2, and then we have to multiply that by its molar mass. So 1 mole of Mg3N2, and then above would be the molar mass. I'm going to calculate the molar mass right here. Molar mass of Mg3N2, that would be equal to 3 times 24.31 grams per mole, plus 2 times 14.01 grams per mole. So let me see what that gives. 24.31 times 3 plus 2 times 14.01. So according to my calculation, and please correct me if I'm wrong because I'm known to make mistakes from time to time, but I got here 100.95 grams per mole. So that number I'm going to put here, 100.95 grams of Mg3N2. So let's see what that gives when you multiply that by 0.4799. So the answer I got, and again, correct me if I'm wrong, rounded off to 4 sig figs, would be 48.45 grams of magnesium nitride. All right? Okay, any questions about this one? Any questions? Any questions? Okay, so that's basically how you answer the A part. All right? Now the B part is asking how many grams of the excess reactant remain after the reaction. Now we know what the limiting reactant is, right? The limiting reactant is the magnesium. So what the question is asking for is how much of the other reactant remains after the reaction is completed, right? So the approach that you would take is you would start off with a limiting reactant, and based on the limiting reactant, you're going to determine how much of the other reactant would be used up. And then once you determine that, you subtract that from the original amount of the other reactant, and that gives you the amount of the excess reactant remaining. Okay. So since I need a space, I'm going to scroll down here. For the B part, what we're going to do is start off with a limiting reactant. So this is the B part. The limiting reactant is the 35.00 grams of the magnesium, right? I'm going to convert it to moles like I did before. So 1 mole of magnesium divided by 24.31 grams of magnesium, right? So the next conversion factor now would be expressing the relationship between the limiting reactant and the excess reactant. And based on the balance equation, the relationship is 3 moles of magnesium down here and 1 mole of nitrogen, all right? And then the next conversion factor is where we convert the moles of nitrogen to grams. So 1 mole of N2, and up here you're going to have 28.02 grams of N2, all right? So let's see what that gives. 35 divided by 24.31 divided by 3 times 28.02. And again, correct me if I'm wrong, the calculation I got, or the result I got, is 13.45 grams of nitrogen, all right? Please note that this is the amount of nitrogen that reacted, right? But what the question is asking for, the amount of nitrogen that remains behind, right? So how do we find that? We take the original mass of nitrogen. So let me just write this down. Amount of N2 remaining will be equal to the original amount of nitrogen, which is 15.00 grams, minus the amount that reacted, which is 13.45 grams. So that's it. The difference between 15 and 13.45. And according to my calculation, the answer is 1.55 grams. So that would be the amount of nitrogen that remains after the reaction is completed. All right? Any questions about this one? Any questions? Any questions? And this question is very similar to one of the assignment questions. Hold on, let me see. Let me see. This question right here, and there's a typo, I just remembered. Number 11 in the assignment, this should be NO2. Yeah, that should be NO2. So please make a note of that. That should be NO2. But this question here, very similar. It's a different reaction, of course, but in terms of the approach, right? Very similar, very similar. All right? It asks which reactant is limiting, how many grams of NO2 is formed, and how much excess reactant remains after the reaction is the limiting reactant is completely consumed. Okay, so you should be able to do number 11. You should be able to do number 12. Let me see here. Number 13. Oh, and that's it. Okay, so far you should be able to do up to number 13. All right. Okay. All right. In the 10 minutes that remains in this class, let me just introduce this topic and then I'll call it a day. Oh shoot, we didn't do. Okay, hold on. Maybe I spoke too soon. Let me go back to the questions that I said you should be able to do. Okay, skip number 12 for the time being. All right. In fact, maybe I should. Okay, let me just discuss this and then we call it a day. So, in an ideal world, when you do these calculations and you do the experiment, if everything works out perfectly, then you'll get exactly what you'd have calculated when it comes to the amount of product you expect to get. But of course, you don't live in a perfect world, right? Sometimes things happen. In fact, more often than not, you won't get all of the product that you expect to get, right? And there are several reasons for this. In some cases, some reactions are reversible, right? So when the product is formed, it reacts to form the reactants, right? So that lowers the amount of product you expect to get. In other cases, the product itself reacts to form other things, right? So that also will reduce the amount of product you expect to get. And yet in other cases, what will happen is you have what are called competing reactions, where you have two reactants coming together, but they form different products, right? So you might be isolating one product, but the other product you don't isolate or it escapes or whatever. So again, that would affect the amount of product you expect to get. So for those reasons, what you'll find is that there's a difference between what you expect to get and what you actually get, right? So the amount of product that you expect to get, that is called the actual yield, right? No, sorry. The amount of product that you expect to get, that is called the theoretical yield, I'm sorry, right? The theoretical yield is what on paper you'd have calculated, and that's what you expect, right? But of course, as I said before, for the reasons I mentioned before, you will get less than the actual yield, less than the theoretical yield. I'm confusing the two terms. So the amount of product that you actually get, you isolate the product and wait, that would be the actual yield, which would be less than the theoretical yield, right? So as a measure of the success of the reaction, we have what is known as the percent yield, which is basically the actual yield divided by the theoretical yield times 100%, right? And in practice, if you do a reaction and you get 80%, you're doing pretty good, right? Because most yields are horrible, right? So that's basically how you determine the percent yield. And in fact, this is what you're going to need in the question I just said that you should skip. So I take that back. So basically, you should be able to do this one based on what I just said. All right? Okay, that's it for today. So let me see here. Oh, so we're not finished yet with this chapter because we have to talk about solutions and molarity. So now the other assignment, assignment number 2. I don't think did I set a deadline date for that?
It's Friday.
It's Friday? Okay. All right, cool, all right. Okay, yes, I did. Okay, all right. Okay, so that's it for today, folks. I'll see you guys tomorrow. Okay.